from Università degli Studi di Milano. The title of his seminar is Entire Functions of Exponential Type in CD and the Geometry of CR Manifolds. With this, I would like to invite him to deliver his talk, and I also request all the participants to mute their microphone. So over to you, Marco.
Okay, thank you very much. Thank you very much for the introduction and for the invitation to give this seminar. It's a very nice opportunity. And well, I'll start with an apology. I'm going to talk about a topic which is somewhat new, but it's not so very recent. So the papers that I'm going to discuss are being published in the last 2-3 years. But I feel like although we have newer results, that in a sense I should start from the beginning because I think it will be more interesting. I believe that I haven't spoke much about these results in general, so I most likely haven't heard anything, and I apologize if some of you have heard already something of this sort, but I don't think so. So, okay, here I want to see, first of all, this talk is based with joint works with Mattia Calzi, and previously with Alessandro Munguzzi and Mauro Salvatori. And so it's a recount essentially of 3 papers here, and I'll show you the reference at the end. And this is the plan of the talk and the topics that I like to cover. So first of all, I would like to recall some of the notions, the property of the Paley-Wiener spaces in one variable, some classical generalizations to several variables, and finally introduce a new approach to these topics in several variables, and a new approach that I think is very natural, and I like it quite a bit, but this is of course my biased opinion. And the right setting, or the natural settings, in our opinion, is what we call Siegel CR manifolds. And this is the new results are on these Paley-Wiener type spaces on this manifold, which I will, of course, explain during the talk. And if you don't know what is a CR manifold, do not worry, but some of you surely probably knows, and maybe some of you others. But anyways, not essentially. Anyways, although the topic is concerns functions, entire function in several variables, the methods of the proofs comes from non-commutative harmonic analysis. So let me proceed. So first of all, I'd like to recall a few things about the function of in Paley-Wiener spaces. So we say that a function, we fix a parameter tau positive, and we take an entire function, and we say that this is a most of exponential type tau. If for each epsilon greater than 0, we can find a constant such that we have this type of estimate. So the modulo of the functions grows essentially at most like an exponential, this exponential growth, and this is the type is given by this the infimum essentially of the constant that I can put here, the exponent. And we to indicate this space of function, we need to put, this is the notation. So the Paley-Wiener space or spaces, and here let me add there are some different notation and definition for these spaces, but in one variable there's, and when p equals 2 here, so I For consistency, I put PW2, and also here, this is what I'll call later, refer later to PW2. So the space of a function of exponential type tau, such that restriction to the real line, and we denote this by 0, f sub 0 are L2 integrable. And we give the norm by the L2 norm of the restriction. And the notation that we use is the following: for when we take y, we denote in R, we denote by f sub y, the restriction of the function of at height y. So we take this function here, this is the line iy, and we take the restriction along this line. Okay, and then one thing that since we are assuming a growth restriction on the function along the real line, then these functions are in fact, they satisfy a little stronger condition. That is, we do not need to take the epsilons here. We also have the stronger condition that the function grows as a fixed constant, and then the type of the functions appear here directly. And also, since these spaces are defined independently, I mean, they are essentially isomorphic for each tau. With simplicity, we take tau to be equals to pi in the next of the talk, and we will not worry about this extra parameter, but the results can be trivially extended to all values of the parameter. This may be relevant to other cases. Now, the classical Paley-Wiener space, and again here, for notations later, you have to think of this as a PW space, because it's the Paley-Wiener whose restrictions at the real line are L2 integrable. And we go here. The Paley-Wiener theorem says that this space, PW pi, is unitary equivalent to L2 of the interval. That is, if we take a function which is in the Paley-Wiener space, then the support of his restriction, the support of the Fourier transform of his restriction to the real line is compactly supported and is contained in the interval minus pi pi. And we have this is Plancherel's formula, and the norm is given by the L2 norm module times the constant of the restriction of the Fourier transform. And vice versa, if I start with the function that is L2 of the interval, I take the holomorphic extension here of the inverse Fourier transform. This is well defined, it gives rise to an entire function. And again, his restriction to the real line is in L2. So this is the classical Paley-Wiener that I'm sure this you mostly know. And we know that the Paley-Wiener space is a reproducing kernel Hilbert space, and the reproducing kernel is given by the sinc function. This is an elementary using the inverse Fourier transform, and we can just see this inverting the Fourier transform of the identity function. We get this. This is the reproducing kernel. And the sinc is the sign over the variable. This is the definition. And we have two more theorems that are fundamental in this theory. First of all is the sampling theorem given by the Whittaker-Kotelnikov-Shannon theorem, that we can recover the L2 norm of a function in the Paley-Wiener space by taking the values of the Fourier transform. Sorry, here there is no Fourier transform. I apologize. This is there's no Fourier transform here. We can recover the value of the function of the norm by taking the series of the value of the restriction at the point n in z. So we can sample the function at the points and the integer points, take the little L2 norm of these values, and this reproduces the function. So this is called the the sampling theorem, but also we have the fact that these kernels form an orthonormal basis for the Paley-Wiener space. Here again, in later, I will have to denote this space with an exponent too, and this is a strong property. We have an orthonormal basis of reproducing kernels. Okay. Then the other is the Plancherel Pólya theorem, and it says that if we go to the height y, the function is again in L2, and in fact we can control the L2 norm of the restriction of the function at the height y by the norm of f at the height 0, so the Paley-Wiener norm, and times this exponential, and this is a strong property and gives the growth of the norm of the restriction at difference line. So here I want to point out some main themes of this research of these theorems, and we are if we start from an abstract point of view, we have a Hilbert space of entire function. We look for conditions that relate the following: the set of the measure or the measure where we require the restriction of the entire function to be integrable. In the case of the real line that we have just seen is just the real line. The sharp growth of the function in this space, and the support of the Fourier transform, or possibly also of other transformations. So again, we have the restriction of the function to the real line, which we require to be integrable. We have the growth, and we have the support of the Fourier transform. So we have these three ingredients, and we would like to see how they are related in different settings. Also, we have seen something about the sampling sets, and also we'll discuss later some condition on the scalar measures. So let me first go to several variables here. Maybe I'm going a little too slow, but anyway, let me go to several variables. So first of all, we have an analog of the function of exponential type. And these already, in several variables, there are many choices. And let me see how I would discuss these many choices. We have much more freedom in several variables. So let's K be a compact, convex, symmetric set with non-empty interior. And this is called a symmetric body. So it's a convex set, which is symmetric with respect to the origin. It's compact and has non-empty interior. So the line will now be okay in several variables. Then in this case, if we restrict to one variable, then there is only there are only the symmetric intervals, symmetric center at the origin. These are the only set that satisfy this compact, convex, symmetric, and non-empty interior. And then we define the polar of this set. These are the vectors in Rm for which the inner product with any x in K is greater than -1. And this is a standard definition of polar sets in convex analysis, but in linear analysis. And if we take K to be the interval symmetric, then this polar set is the interval minus 1 over K, 1 over tau, 1 over tau. And if we take in Rm now, instead, we take this type of balls with the exponent P, it's cross ball, then its polar set is given by the same condition, but with the exponent, the P prime, so the conjugate P prime. And when we have a symmetric body as above, we can define a norm on say on the dual space, in fact, and the norm is defined by the sup of this inner product when X is in K. And K naught then is the unit ball with respect to this norm. So any convex, again, any convex set, you define the polar set, and then the polar set becomes the uniball with respect to a norm. Okay, and then if we have such norm, we can extend it also to CM. So far,
Can you go back to previous slide? So this norm is on cannot pull up. Can you go back to previous slide?
On RM.
Oh, for any, okay, for any J belongs to RM, okay.
So here we are on RM, yes. So far we are just on RM, so the norm here is C in RM, sorry, yes. So far we're just in RM. And, but then I can also
So X belongs to this cannot or this X belongs to K or cannot for this? Because the thing is, you are just taking X belongs to K. Is it correct, I think?
I'm not understanding the question, sorry.
So this norm J with respect.
This norm that I defined is a norm in RM and is defined, well, taking this soup. I fix, I take a C vector in RM, I take the inner product with the elements in K, and I take the soup.
Okay.
And this define a norm in RM.
Okay. Okay. Okay.
Okay.
Okay. Okay.
But then I can extend this also to CM. CM to extend it. So I take a vector. Now I take the modulus of this inner product. Z is, of course, the inner product is defined between also extend to linearly to CR linearly to CM. Z times K, and I take times X, and then I take the soup over X in K, and I define a norm this time in CM. Okay, so and this is a way to, in fact, and also it's true also the converse. Every norm arises in this way. There is always, if you give it a norm, you can construct a set K, and it is polar, and you can define every norm can be described in this way for some K. Now, given K is above, then we define this growth. So the growth is given now in terms of K. So instead of having a real parameter here, I have the parameter here is given by a convex body. And I take the norm, and the growth here is, of course, these are all equivalent norms because we are on a finite dimensional space, but it's important to have well, the growth. So the growth here is measured in terms of this norm, and since I built, in a sense, I built what was before tau is built in the norm here, and this is the soup. And so I take 1 plus epsilon, and this is I define a norm and a growth and a condition, and these are E sub capital K. K is a convex body. Then I define the Paley-Wiener space, and again here I should write 2. It's this time here, but I will come back to this later when I introduce all the spaces. So the Paley-Wiener space is the space of its function of its entire type of type K as above, whose restriction to RM is L2 integrable, and we have this condition. And now the Paley-Wiener theorem generalizes to this situation. This was originally proved by Plancherel and Pólya, but you can find a very nice treatment of this in Stein-Weiss book on Introduction to Harmonic Analysis of Euclidean Spaces. And again, the Paley-Wiener space consists precisely of the homomorphic extension of the Fourier transform of function of L2 K naught. So K naught is the functions are supported on the L2 of the function are supported on this polar set. And sorry, here, scroll. Okay. And also conversely, so if the function is in a Paley-Wiener space, then the Fourier transform of this restriction is contained in K0, and we have equality of norm. And if I start with the function which is L2 of the polar of this convex set, then the holomorphic extension of the Fourier transform gives rise to an entire function. And again, of course, we could go back and have equality of norms. And there is an analogous of the Whittaker-Kotelnikov theorem for when K is a symmetric hypertriangle central at the origin. In general, if I have a general symmetric body, then the analogs of the sampling theorem is not so clean. And I will skip here. But now I want to introduce a new notion of this in several variables, which is not as simple as this one. And the idea is the following. I start with, so I'm in Cn, and here I don't need to write to drive. So anyway, or in CD, now I'm in Cn plus 1, as a matter of fact. In any event, I take a hypersurface. Let me delete this. I take here, I take M is a hypersurface in CD in general, or let's say in Cn plus 1. And the requirement is that if I restrict the function f is entire in some sense, so it's holomorphic in Cn plus 1, and I take this restriction to M, I require it to be L2 integrable with respect to some measure, which is a natural measure. And that's the idea. So if we go to several variables, the idea is to restrict to the hypersurface, not just as I did in the previous case, to restrict to the case of Rm when given before we were in Cm. I restricted the function to Rm. So I put somewhat the imaginary part to 0, and I look at the restriction to Rm. But this is somewhat not very natural in several variables, and it seems more natural to have a slightly different approach. So I start from Cn in Cn plus 1, and I take the submanifold, which is given by these points, where the imaginary part of the last variable equals the modulo square of the vectors. Zeta is in Cn, so it's a vector, and Z is that is a scalar, and we have this. And this, in fact, is as set is the Heisenberg group, and in fact we can parameterize it at this submanifold, this hypersurface as Cn cross R, and we're going to see this. So we identify the point on the manifold in this coordinate with zeta x, where x is the real part of Z, so that the point Z is exactly x plus I mod zeta square. And we have a natural product, which is given some biholomorphic mappings, but here let's not dwell into that. And the product is this, and this is the Heisenberg group. And on the Heisenberg group, we do not take, so on the hypersurface that we just selected, we do not take the induced surface measure, but we take another measure, which is natural also from the point of view of complex analysis, which is the hard measure on the group, and again, which is not the induced Lebesgue measure, but it's very natural from the point of view of Tanaka-Webster connection, but I'm not going to go into that. And here are the Paley-Wiener spaces. So now, again, if I don't put the exponent, you have to think here there is a 2. But I'll see, because now I'm going to go also in P different than 2. So again, the Paley-Wiener space is the space of entire function exponential type, such that when I restrict it to the submanifold is L2 integrable with respect to the R measure, which is again the Lebesgue measure in Cn cross R, which is the R measure for the group. And if P is in 0 infinity, we call this space the Bernstein space, and we denote it by P, Pk. This is a K, I'm sorry. This is a K again. Also, this is a K. Is defined again as the space of entire function exponential type K. So kappa, sorry, I'm mistaken here. I'm going ahead of myself. We have with kappa. Such that the restriction is in LP with respect to this measure. And, oops. Now, we call these spaces the Bernstein spaces, but there is no complete agreement on the names of these spaces. So many authors call these also still Paley-Wiener spaces. That's why I have two notation, but I'll be, should be no confusion. So now we set the space to be given by the LP norm of the restriction with respect to the R measure. And now we also have, by means of the we can prove Plancherel-Pólya inequality gives us a little more, show that there, in fact, we can allow a stronger growth in some directions of the Heisenberg group, the so-called complex tangential directions. Let me also here give this definition now. So again, here I have still a kappa, and I'll go to the convex body later. So we define a height, which is the difference as a function in Cn plus 1, is the difference between the imaginary part of minus of z minus the modulo of zeta square, which is the defining function for the domain. In fact, we define the space of entire function of type kappa, the entire functions for which for each epsilon there exists a constant for which we have this growth. Notice so that in the direction of the real part of z and in the vertical direction, you should think of h as the vertical direction because if I, so this is now the Heisenberg group that sits in Cn plus 1. So h measure is in fact, it could be positive. This here is h is positive, the imaginary part, and here when h is negative, and of course this is h equals 0, the height. And so this function that we're considering can grow linearly, just in the exponent here is linear in the direction, the real part of z, in the vertical direction, and is also quadratic in the complex tangential direction, zeta. Now, of course, what I draw earlier here, this is the APRG space, is the Siegel APRG space. And now we have this definition, again, the Paley-Wiener space, as it was indicated before. Now I introduce the P. And I can use this notation or this notation here, the function that are exponential type, where I allow also, again, this quadratic growth in the complex direction, complex tangential direction, and the restriction to Hn of the function is Lp-integrable. Okay, so this is our definition. We have set up the submanifold, the APRG surface. We have set up a measure, and we have an exponential growth. And here we have now our first, the Plancherel-Pólya theorem.
Just
Yes?
a very simple question. Like the Euclidean case, actually, the thing is, Paley-Wiener space has really, the thing is defined using this Fourier transform. Okay, it has really connection to that. But in this specific case, does it have some connection?
Of
this
course,
Heisenberg?
of course. That's the content of the. I'm going to get to that. Of course. Yes, absolutely. That's the idea to show that, in fact, that's what I wanted to show you. So I'll start with the Plancherel-Pólya inequality. And here again, I take the function f, and I restrict it to the height h, as I did before. Now, this was the Heisenberg group. And do it here. This is the Heisenberg group. I take this h and this copy, this, so f will be at this height, and this is the variable, the analog of the variable on the Heisenberg group. And and here is the condition that if we integrate the p norm at height h is controlled by this exponential times the p norm at height 0, so the Paley space. And so here I have an exponent, and in the classical case, here I would have e to the kappa mod of h. So whether I go up or down, here I would have this growth. But in the case of several variables, in this situation, this exponent is always positive, and but it says that sorry, no, it's not always positive. 0 is the minimum, but it says that in fact, if h goes to if h is positive, the minimum, of course, is 0, and so this says, look, if h is positive, so it takes the restriction here, there is no growth because the minimum is 0, and so all this, the integral over these copies of the Heisenberg group are going up, they are all bounded by this, so there is no growth in this direction, while instead the exponential growth of the norms appears only if h goes to minus infinity. Okay, so and the fact is that in the case of Rn, there is no difference. The line the hypersurface is flat, so there is no, in a sense, there is no difference between the inside of the domain, the upper F plane, or the lower F plane, which we consider as the outside of the domain. But in several variables, in this setting here, of course, there is much difference between being inside the domain U or being in the complement of the domain U. And there is, because there is a curvature on the hypersurface. So let me go now. First of all, the Fourier transform. Maybe you're more familiar with the Fourier transform of the Heisenberg group. And so I introduce first the Fock spaces, which are spaces of entire functions, this type, which are integral with respect to a Gaussian decaying weight. And we have the Barnard representations. We take functions of the Fock space, and we multiply by and translate by this vector. These are so-called unitary representation, a unitary operator on F lambda. And well, this is defined in this way. I hope you're somewhat familiar with the Fourier transform on the Heisenberg group. Now, if F is in L1 of the Heisenberg group, the Fourier transform is defined as an operator acting on the Fock space in the following way. So we take the function and then we integrate again this weight, and this is so this gives rise to another function, and this is in fact an operator. In fact, is a Hilbert-Smith operator in general. Oh well, this is an operator on the Fock space. So it's acting B lambda F, which is the Fourier transform of F with parameter lambda, and is an operator. It's not anymore a scalar. It's an operator on the Fock space. And so if F is in L2 intersect L1 on the Heisenberg group, then B lambda f is the Hilbert's mean operator, so I needed the condition on L2. Is a Hilbert's mean operator on the Fock space, and we have this Plancherel formula. And this is a measure which is relevant. It's called Plancherel measure. And then the inversion formula, if we start from the Fourier transform, and we take the trace of this operator, which is a Hilbert's mean operator as in a trace, and I take the inverse Fourier transform, and then I can recover Z F at the point XZ on the Heisenberg group. And okay, here, this is our, sorry, this is already seen all this. Okay, now I define script L2 as the function defined on R star as R minus 0, and goes into the product of Hilbert's mean operator on the Fock space F lambda, and this is the norm. So we take the Hilbert's mean norm of tau lambda squared, and we integrate with respect to the Plancherel measure, and this is a norm on this L2 space. And we also need the holomorphic trace of this space, which these are the functions in L2. The satisfied two conditions are supported when lambda is negative. So tau lambda is 0 when lambda is positive. And the range of these operators is contained in the span of the constant. So no matter what we apply to tau lambda, then we have, this is a span of the constant function. Notice that the constant function is in F lambda. It's holomorphic and is L2 integral with respect to the Gaussian measure. And this condition, of course, is only when it's not 0. Otherwise, it's trivial verified. And well, if E is a subset of R, then H2E is the space of the function, which is in this subspace of L2, whose support is contained in E. This space is now, it's late, let me skip. There are some conditions that arise from the analysis of Hardy spaces on the Heisenberg group in terms of the Fourier transform. Let me skip this. And this condition here also arose in Ogden-Vaghi theory. But again, I think I'm late. I'll skip this for a moment. And now again, recall that we have this notation. And so here's the theorem that you were just asking me about. So if I take, here again, we are in the Hilbert case. If F is in PW2, so L2 integral, then the Fourier transform is in H2 of 0 kappa. And if we can recover the function with this trace, and the Fourier transform, again, the L2 norm, this is essentially just Plancherel theorem. Conversely, if I start with the function, which is tau, let me go back here. I just noticed that I made a change. I apologize for this. I made a change in notation here. I want to, this is a normalization. So I want this to be, I correct myself, not when lambda is positive, but when lambda is negative. And here, this is just a normalization of the Fourier transform. So H2, I want to have it set up in this way. So the function tau is 0 on the negative F line. And when it's positive, the range is contained when, again, in the span of the function 1. I apologize for that. So let me go back to our theorem, because again, here I use the different normalization. So suppose that the Fourier transform is supported on the interval 0 kappa, then, sorry, If F is in the Paley-Wiener space, its Fourier transform is supported on the interval 0 kappa, and also satisfy the condition that the range, when it's positive, the range of this operator is contained in the span of 1 of the constant. And well, of course, we have this representation by the inversion formula. Conversely, if I start a function which is L2 as supporting this segment and not in the other one, and also as the condition on the range, then we can in fact construct an L2 function. Here we have the holomorphic extension. We have this extra term. If I didn't have this term, I would just reproduce the function. I would just produce a function in L2. But here is the extension, the homomorphic extension of the inverse Fourier transform, as in the case, the scalar case, in the one-dimensional case. And this function is in the Paley-Wiener space. Of course, the Fourier transform, this is now is just somewhat Plancherel. The Fourier transform is the function tau that we started with, and we have equality of norm. So this is the answer to your question. In fact, once we set up the question in terms of the Heisenberg group, I mean the restriction of the entire function of the Heisenberg groups to be L2 integrable, we get this very, very natural theorem, extension of the Paley-Wiener theorem in terms of the group Fourier transform, and that was what made us believe that we were doing something very natural, because we could connect the Fourier analysis on the Heisenberg group, the Fourier transform, in the very, very same way as in the one variable case. Okay, we do not have a complete orthonormal basis. We cannot find a complete orthonormal basis of given by reproducing kernel. Of course, we can write down the reproducing kernel in terms of a sinc function, and I'm not gonna go through that here, but this is very natural and uses the same quadratic form that appears in the Siegel kernel. But let me skip it here maybe. And anyway, let me just discuss instead of the sampling theorems that replaces again, it's the Whittaker-Kotelnikov-Shannon theorem. And here's the theorem. So we take a lattice, and in Hn, they satisfy, given by this definition, gamma is here. So it's made, the points are in the points, didn't write, where is, oh. So these sets here are sampling sequences for the Fock space that I don't describe explicitly, but they are not well known as they are. Notice here kappa, and these are sampling sequences for the Fock space. Then I take the Cartesian products of this sampling sequence. Then I take in the last variable, I take a suitable multiple of z, and I take this lattice. And this lattice now is a sampling sequence for our Paley-Wiener space, and this is the condition. So the norm is equivalent to take into the evaluation of the function at this point. And there is no equality. The reason is not as precise as in the case of the line, because we have only an equivalent of norms. But still, this is pretty nice, we believe. Okay, now I only have a little bit of time, and so I want to go through now the generalization to more general CR manifold, because this is the last thing that we introduced, because I want further generalize from the case of the Heisenberg group, where again everything comes very natural, to more general submanifolds. And so here briefly, what are CR submanifolds? There are these are manifolds for which there is a complex subbundle of the complexified tangent bundle of the manifold. So we take this the tangent bundle, we complexified, and we want to we require the existence of a subbundle such that is integrable in this sense, and there is no intersection, non-trivial. The intersection between L and L bar is trivial, and if f is one function on this manifold and is annihilated by any of the complex bar, the bar of all these vector fields, these are the tangential conjugate Riemann equation, and f is called the CR function. And well, if omega is a domain in CD and its boundary then is a CR manifold of dimension, or CR dimensions d minus 1 and real codimension 1. And this is so-called also the hypersurface type. And L are the tangential homomorphic vector fields. So here I want to take some particular CR submanifold, not necessarily of hypersurface type. So I go to, if I take a form from Cn cross Cm into Cm, and this is a Hermitian mapping, and so I take the points in Cn cross Cm, and I take this difference. Notice now Z is a vector, not as in the case of the Heisenberg group. This will be M will be 1, so this will be a scalar, and this will be a scalar value, and phi will be just the modulo of Z squared. Phi Z will be. And this is a quadratic CR manifold because it's given by a Hermitian mapping. So it's a quadratic in zeta. And so here the CR dimension is n, and there's a real codimension m. And we have this notation. Then I want also to say, sorry, I went further. I wanted to say that point out that phi, in fact, is the vector value Levy form on the manifold maps. Then for this phi takes a bunch of conditions on carries a lot of information of M, of course, the Levy form, and we have the scalar. These are the scalar valued parts of the Levy form. As lambda, we take a vector in Rm, and we take this inner product. But now I'm going very slow. So there are many papers that concern the Kohn-Laplacian on forms on these CR manifolds. In particular, what plays a role is the existence of vectors lambda for which this form is not trivial. So that for every z, this function is actually positive definite. So this is so if lambda plus this vector is not empty, then M is called a Siegel quadratic CR manifold. And in fact, there is, again, is a condition, is a sort of pseudo-convexity condition, a vector value. Okay. In particular, there is a connection to say that okay, this cone is not empty means that there exist lambda prime vectors in Rm, such that as a phi lambda has n negative eigenvalue and phi lambda prime has an n negative eigenvalue. So the equivalent to say that the Kohn-Laplacian on M has non-trivial kernel on zero forms. But and in this case, M is the Shilov boundary of a Siegel domain of type 2. This entered this play. And this would be the domain, but let me go further. So, okay. So now we play the same game. We take copies of this manifold. We translated this time not by a scalar, by an element in Rm. then this sets foliate the full space CM cross CM. And again, we introduce coordinates before. We take imaginary of Z minus the form. And now this we have coordinates on M. Now notice that this is in Cn and this is in Rm. Okay, and this again, we form an analogous of the Heisenberg group is a two-step Lie group. Again, it plays the Fourier analysis on this group plays a fundamental role. And from here on, you can imagine almost what is going to happen, although we need to introduce the support function of a compact convex body. And this, again, as before, we take this soup. This, again, is we are in Rm. And this is the soup function, so it's connected to the polar. And again, we take the modulus. Here, we have this term here. And we have the defining function. And we have this function here, h, the support function. And again, we define this time, it's defined in terms of the convex body K, kappa, K, and the space of entire function, which we have this growth. And again, we have a quadratic growth in the complex tangential directions. And let me, well, here a few examples, very simple, but when K was as before, the interval, the F interval, 0 kappa, then the support function was exactly what we found before, with multiplied by kappa, but with the minimum between 0 and h. So, and this was the case that we had before. So this is the step, this function here replaced this minimum that appeared earlier. And so this is the support function, which was less intuitive than one expected, but although it's very natural. And now we have this somewhat of the same theorem again. And now I'll probably go again even faster, but here we define the Paley space in the same way. We have defined a growth of mod. Of course, look at the, again, I want to point out that the growth of the function is related, is dictated by a set K, is a convex body, and which for the time being is disjoint by M. And here we have this definition. So we fix the growth and we fix the function and the integrability along M. But now we, first of all, we have a bunch of conditions. So these spaces are non-trivial if and only if K intersects lambda plus with as non-empty interior. And in fact, then we have this equality. In fact, what matters is just the intersection of K with lambda plus. But if in case K does not intersect lambda plus, the spaces are trivial. So there are no entire functions of exponential type whose restriction is none, besides the trivial function. So, and I want to say this, I didn't say this earlier. So in the case of the Heisenberg group, we consider the support of in this 0 kappa. But if we had taken the set K to have non-empty intersection with the opposite, so we had taken something on the other side, like say minus kappa 0, then the space that would have implied that this WP was just trivial. So if we had taken something on the negative interval, on the negative F line, then the space would have been trivial. And this is the content of this, even more in general, of this result. But then let me go, let's keep this in its quality. Let me go back. So to the main theorem, again, anyway, the Plancherel Pólya says that the growth of the function, of the restriction of the function at height h, again, h here is a vector, but still is given control by an exponential times the LP norm on the, this is just the norm on LPM, and this is the exponential factor, but it's controlled, there's this support function. And this in particular is important because it says that these spaces are complete. And now let me really skip here. We construct the harmonic analysis with the analogous of the Barman transform, and we have a Fourier Plancherel formula again. We have the inversion formula again, and now this is the last theorem that I'm gonna present. Is again, if K is a compact convex set, is contained in the closure of this this cone where the Levy form is positive, then if F is in the Paley-Wiener space, then its Fourier transform is in H2K as indicated before, and it holds this is again with a period of this exponential. This is the holomorphic extension of the inversion Fourier formula, and we have the Plancherel identity. And then conversely, if we start with the function which is in H2, okay, and again, well, it means that it's supported on K's and is L2 integrable, and the range is contained in the span of the constant. Then we define F as an entire function on the whole space. But it means the Fourier inversion formula extended with holomorphically. Then this function is in the Paley-Wiener space. The Fourier transform is tau, and again we have the formula. So again we have the Paley-Wiener theorem in this setting, and goes perfectly again as in the I mean, it's a very natural extension of the scalar or the one-dimensional case. And I went so slow. I have bunch of other results, but concern sampling and counts of measure theorems, and also the projections. But again, I'll stop here.
Okay, thank you, Marco, for a nice talk. Are there any questions from the audience? There is a question. Yeah. Thangavelu sir, you want to ask a question, sir? Hello. Dheeraj, you may ask your question.
Yeah, thanks. My question is that in the initial slide, when you were discussing the PW, the PW results, so in the first slide when you just defined the PW set, so there you mentioned that like a function which is like upper bounded by exponential of tau plus epsilon for any epsilon greater than 0, then
yes,
if it is also if it is a PW function, meaning that if it's restricted to real, it belongs to L2, then essentially we can upper bound it by some constant times e to the power tau. We need not have that plus epsilon. Yeah, e to the power tau mod z. So like, so if it does not belong to this set PW tau, then are there cases where we cannot express it in this form, but we can express it in the first form, meaning that for every epsilon we can have the condition that it is upper bounded
yes,
by?
for instance, I mean, I guess you meaning that if this representation is necessary for function of entirety. Right. Okay. Yes. For instance, just take the function f and which is in the Paley-Wiener space and multiply by a polynomial. Then is not going to be L2 anymore in general, because the function will not decay sufficiently fast to be still L2 integrable. Take just the sinc function, which is in L2. The sinc function is, say, take a sine of z divided by z. This is an LP. This is it. But if I multiply by a polynomial, this will not be in L2 of the line when restricted, right? When it's restricted to the right. But then this inequality is impossible now, because again, in some direction, I mean, because it will not be, because you have this extra term, and to bound this extra term, you need to get some epsilon. It will be true for every epsilon. You find a constant. Of course, it depends on epsilon for every epsilon, but you cannot take epsilon equals 0 to bound this function here, because again, you just
that's constant.
Yeah.
Right.
Did I answer your question?
Yeah, got it. So basically it's lesser than every exponential, but it's not upper bounded by a constant.
But you
so then
just
we need not have a sine z by z, right? We could have just taken any polynomial which is not bounded. Any non-bounded polynomial would have worked, right? Or do we need that sinc function as well?
No, I don't understand your question. Sorry. I'm just saying that so this is just the type here, because taking, of course, if we instead of having this constant here tau, you put tau plus 1, then I mean then of course you would have this type of bound. But if you want to reach the infimum, so if the infimum is a minimum, then you in order to you need to have some extra condition, and the extra condition in this case is the integrability along one line. So if you impose that, so the integrability along one line, then you have this stronger condition. So the infimum again becomes a minimum. But of course, if you're not aiming to have the minimum here, you can just, instead of putting tau, which in this case would be 1, you put 2, and that will be enough.
I see.
Okay.
Okay. Yeah. Thanks a lot. That really helps.
Sure.
Thank you.
I have a very small question. The thing is, the norm with respect to this bipolar, you are taking this thing.
Yes.
For instance, if you take this k is really the unit ball in Cn, what will you get this k norm?
If you take the standard unit ball in Cn, then you get, but then you have to have. So there are two different type of situations here in several variable. First of all, you go to Cm, and okay, and here, and you use the Euclidean Fourier transform. So in this case, if you take the ball, then you, of course, you get exactly the same. So if here take p equals to 2, then its polar is again p equals to 2. Its polar set is just the sphere, and that's the standard situation. But again, there are many different cases. I mean, that are allowed if you take different norms, and of course, then the polar sets are different.
Okay. So
yeah, you recover the natural, the standard case if you just take the regular ball.
So it may happen that 2-3 convex sets, means many convex sets, can give rise to a single norm. It may happen, or this.
No. If these are in fact, the bipolar of a set is again is actually the convex hull that you started with. So if you start with K, you take K naught. This is a convex set, but even if K is not convex, but then if you take the polar of the polar, you get K. In the case K is convex. So if you start with a convex body, then there is a unique one-to-one correspondence between the polar sets.
Mm-hmm.
So there are no. If you start with the convex body, then the norm is uniquely determined, or vice versa. If you take a norm, is uniquely is the polar of unique set in a convex set.
Mm-hmm. So the thing is, another thing is you said something hyper triangle in your talk. What is that? You said some result about hyper triangle. You said some result about hyper triangle.
Triangle? No.
Yeah.
No, I don't know.
Can you go next, probably in the field, please?
Next slides.
Yeah.
Oops, why am I going so fast now? All right. So here I'm going backwards. Let me tell me.
Yeah. Hyper rectangle. Sorry, not hyper triangle. This is a hyper rectangle.
Okay, so if you in the case of hyper rectangle, then basically this in our end, then basically you just reproduce the Paley-Wiener theorem in each variable separately. Because so you have hyper rectangle, then in each direction is the hyper rectangle is a Cartesian product of intervals. And so in each interval, you repeat the Paley-Wiener theorem in one variable. Mm-hmm. And so that's easy. Then you basically just iterate the Paley-Wiener theorem, then the Fourier transform. So if you start with a hyper rectangle, then you go. Then you do. So here, this is in R2. This defines the norm, and you use this to define the norm. Is dual norm is I believe is sort of the rectangle in this way. Then you basically again you get the F is in a P W. Say the upper rectangle is called capital R. If and only if this is a 2, the Fourier transform, the support is contained in this polar set, which is easily computed, and that's again, this is R and this is R prime, and so it's easy to do it. Yes.
Mm-hmm. I don't. Thangavelu sir wanted to ask you some question, but he is unable to unmute. Okay. So Thangavelu sir, are you there? Yeah.
I have a couple of questions actually.
Okay. Sure. Yeah. Ask.
Yeah. So, you talked about something when you're talking about this Paley-Wiener theorem for the Heisenberg model. You have something like Hardy spaces on an interval, right? It's kind of like some 0 to kappa. It's sort of is it kind of a Hardy space of kind of an interval? I didn't get that point.
Yes, so if Hogenwege theorem basically describes, so in that sense we have nothing really, so I mean we follow some of their ideas, and let me see if I can find the slides. Transform, okay. So if you you go, all right, let me see, sorry. Okay, here it is. So if you start with the function on the Siegel FRF plane, so here this is U. Let me use the pencil. So this is U, and this is the Heisenberg group. Then you take the function which are holomorphic on the domain, and you take the sup of the restriction of the norms over the translated of the copy of the Heisenberg group at H at IH, and this is finite. Then this is the called the RD space, and then if you go to the Fourier transform, then I'm using this other normalization, and yes. So no, this is correct. This is what's the correct normalization. So if we take the function in the Hardy space, then the Fourier transform is 0 when lambda is negative, and the range again of the Fourier transform is supported in the span of 1. So this particularly means that the support of the Fourier transform is contained in the positive F line. So all of the F line. So if you want to take the closure, you take but in the case so a subspace of this, of course, you would take the function that was Fourier transform is supported on an interval 0 kappa. And those function here, now I have exactly the function in the Paley space. So what I'm saying here is that I2, in the case of the Heisenberg group, this of course is closed subspace of the space of H2 of U. All right, okay? Because again, I characterized by the ones that are this support is contained on an interval, and this is also in the case of in the Euclidean case. I mean, if you go into the Euclidean case, I'm doing. If I go, I also have my. Sorry. So if I go on the this is in C, and then F is in H2 of C plus, which is this, which is analogous of U. An analog of U is the upper F plane, and then the support of the Fourier transform is contained in 0 infinity. But if I take the support of this in 0 pi, this is now this implies that F they started with is in Paley space over the degree pi. It's not the whole space, because this will be characterized by the support on the whole interval minus pi pi. But in the case of the Heisenberg group, where things are asymmetric between the inside of the domain and the outside of the domain, then all of the subspace of this one is actually, if I restrict the Hardy space to have support of the Fourier transform only on the interval 0 kappa, then I get the whole Hardy space. I hope I answer your question.
Yeah. Yes. I got it. Yeah.
So Agniva, do you have other question?
No, it's fine. Yeah.
So are there any other question from the audience? Okay, if not, let us unmute and thank the speaker for a nice talk. Okay.
Thank you.
So the thing is, let me stop the recording. Okay.
Yes. And you have
Okay,
my
so
permission to publish the recording.